Now that we've defined the first law of thermodynamics, we have a series of applications to show what we can do with it. So first, we're going to determine the thermodynamic properties of gases. Again, taking that outside-in approach, just using macroscopic measurements of pressure, volume, temperature to understand properties of our gases. We'll find in the course of that defining the heat capacities Cp and Cv is very useful to understand and calculate properties of gases. Next, we'll go over 4 common gas processes. So these are different changes we can apply to our gas, and we'll see how we can use the first law in a systematic way to do careful accounting of all the different ways energy flows in these processes. These are useful for applying the first law, and they're also very useful in applications in chemistry and engineering, different containers, constant volume, constant pressure, different ways that we can transform our gases. Next, with all of this information about gases and how they change into these different processes, we are going to explain and rationalize molecular properties, again, connecting these macroscopic properties of gases back to the microscopic, so particle size and molecular forces, things like that. This red goal we'll get to in sort of our next section, but that's where we're going. Okay, the plots below were made by doing this sort of experiment. Each gas is in a sort of Dewar container with a constant volume V, and we have a resistor to be able to do electrical work on the gas, running a constant current through it. And from that experimental data, we're able to determine the internal energy versus temperature, because we're continuously measuring the temperature and pressure, and we're showing internal energy, temperature, pressure. We have the initial pressure P naught. On the plot, we're not showing the pressure throughout the experiment, but we did measure it. We could keep track of it. So here are the results of these experiments for neon, for argon, for N2 and O2. Again, I'm showing on the y-axis the molar internal energy. This should really, I guess, be joules per mole of gas on the y-axis unit. And then the x-axis is temperature. I started at 200 Kelvin. And since, energies are all relative, I'm just going to assign each of these gases an energy of 0 at 200 Kelvin. So that's what we're sort of plotting here, is energy versus temperature from the result of this experiment. That's what we can get from thermodynamics, is we can get this macroscopic information about how energy varies with temperature, and we'll sort of see some of the things we can start to do with that. Okay, so first, how do I use the experimental data to make this plot? Well, I have the current, resistance, and time. From the previous set, again, we're going to do our full first law analysis, so delta U in general is Q plus W, which in this case is Q plus work electrical plus work mechanical. We always need to worry about work mechanical, and, obviously Q we'll figure out, and in this case we do have electrical work done according to this current and resistance. So let's start dealing with those terms one by one. First, Q is equal to 0 because we're in that Dewar flask, which we can assume adiabatic walls. Okay, that's nice. That turns one of those terms to 0. Work mechanical is the integral of P external dV negative. In this case, if we think about the container that we have, our container has a constant volume. So we're integrating from VI to the same final volume, which is also that same, volume VI. We can view this as basically dV is equal to 0, and the overall integral is equal to 0. No mechanical work if B is constant. So again, because we're integrating from the same initial to the same final, work mechanical is equal to 0. Again, we can think about that as sort of setting dV is equal to 0 here. And yeah, we have no work done in this process mechanically. The final term that we have is work electrical. In this case, we can use the equation derived at the end of last set of notes, as work electrical is integral of I squared R dt from my initial time to my final time. And that's going to be equal to I squared. My resistance R is 1.5 ohms. And then my dt here, right, this should be t. I squared and R are constants, they get pulled out of the integral. Then we have the integral of dt from ti to tf, which is equal to, in this case, just the time t. We're going to say t I is equal to 0, t f is equal to t, and so this is just going to be equal to I squared 1.5 ohms times t. So we know this current I, whatever it was during the experiment. We know the resistance. We're keeping track of the time. Maybe we're collecting data points on the pressure and temperature every 1 second. So this will let us now know how much electrical work we did at each point. And that will then also tell us what delta U is equal to, since delta U is equal to just the electrical work. And again, we're going to assume the thing we're doing here is we're saying UI is equal to 0. By sort of assumption, that's what that's our sort of 0. And so as a result, we're going to say that the internal energy of my gas is equal to the electrical work that's going to be done, which is equal to I squared times that 1.5 ohms times T. So pretty simple. We know the current, we know the resistance, we measure the pressure and temperature at each time, and that will give us the internal energy versus time as shown here. Okay, so now that we know how we were actually able to measure internal energy versus temperature, what do you notice about the molar internal energy? Take a couple minutes, take a second to try to look at those graphs and figure out what you see. There's a lot of different conclusions you can draw from that data. If you're tracking it carefully, you should be able to make at least 3+ key observations answering this question. Okay, so here's what I got. The first thing I would say is that all of these, if we look at them, are that they're basically linear. So linear, basically a constant slope on this graph of energy versus temperature. That's useful to know. It's not always the case, but for these gases, under these conditions, it seems to be the case. Okay, the second one that might be a little bit more subtle is if we look at the effect of the pressure, we have 5 different lines here. Those lines in each of these cases are almost exactly on top of each other. So pressure has little effect on the molar internal energy. All these lines are basically the same. There's actually a slight difference for argon, N2 and O2. We can see there's actually a slight difference. We could, if we sort of zoom in, we could zoom in and see, okay, there's slight differences between these different lines. Purple, slightly lower than say red here, right? Slight differences, but again, for any perspective purpose, pretty much similar, right? Purple line is an initial pressure of 10 bar or 10 atmospheres, much higher initial pressure. Almost no difference though, right? So that's sort of what we have going on there. Pressure has little effect. that's pressure's little effect on U bar. No effect that's discernible for neon. Again, we're making these sort of macroscopic observations. These are almost the exact same. Neon, we can't detect any difference. If we zoom in, again, maybe there's a tiny difference there. We can see a tiny hint of red peeking out, but almost no difference there for neon. Whereas for the other three, there's at least a little bit of difference between the lines. You know, it's small, but there is some difference. Okay, the last one, how are O2 and N2 different from AR and NR? Well, we can see here that neon and argon have a certain sort of slope. N2 and O2 have a larger slope as well. So O2, N2 have a larger slope. The slope of O2 and N2 is very similar than argon and neon, which also has a very similar sort of slope. So again, putting us back in history here, this is really how thermodynamics is done. We do these measurements, we make these macroscopic observations. It turns out that these diatomic gases have very similar behavior. Argon and neon, monoatomic, have very similar behavior in terms of their internal energy versus temperature. There has to be some reason for that. Again, where we're headed here, right, is that we've now made some macroscopic observations. We've got to be able to connect that back down to the microscopic differences between neon and oxygen. How is energy distributed in those different molecules? What energy levels are occupied? Again, we just went the opposite way in the previous homework, but again, now we have this macroscopic data. Let's see what we can learn from that. We see these very different behaviors in macroscopic energy versus temperature for N2 and O2 versus AR and NE. Okay, so again, from these macroscopic observations, knowing that the slope on these graphs is pretty constant, that motivates us to, hey, the slope of the energy versus temperature graph is probably going to be a useful thermodynamic quantity. It distinguishes these diatomic from monatomic graphs. And so in doing thermodynamics, we can now define that. Let's define the constant volume heat capacity. So this is called CV. We didn't need to know that name coming in, but the idea is that, yeah, the slope of energy versus temperature is a really useful thing to keep track of. These are partial derivatives because energy depends on many variables. But again, all we're doing is we're saying holding volume in moles constant, which is what we did on the previous graph. If we take the derivative or the slope of the energy versus temperature graph, that will give us this heat capacity. So again, how we get that, we're taking the, again, since we're taking the derivative, right, slope of tangent line at each point. That's easy to do in Python, or we can approximate it in Excel. We'll find that, right, since this is basically the derivative of u versus t, is my CV, right? Again, I can say that that's approximately equal to delta u over delta t over some little area of that graph. So again, if I had a graph, I'll pick one where it's changing a lot more. Okay, if I take a little bit of energy, delta u, a little bit of temperature change, delta t, that'll give me the slope at this point. Again, maybe at this other different point, maybe up here I have a slightly higher slope. Delta u is a little bit bigger for the same delta t, so now this is going to be a slightly bigger heat capacity, a slightly bigger slope of the tangent line at this point compared to at this point, say. Okay, so from that, now we get a really useful result. We saw that it looked like the slopes of those lines were pretty constant, and that is in fact what we see. When we take the derivative, this gives us a lot more fine-tuned information. Argon has a slope. I'm plotting it in these units here. We'll see why in a minute. So this is the molar heat capacity divided by R, the gas constant. The molar heat capacity, CV, is in units of joules per mole Kelvin. It's the same units as our ideal gas constant R, and it turns out that these are sort of nice round numbers when we divide by R. That's just sort of an observation that we had to make by people doing thermodynamics when they were sort of discovering this field 100 plus years ago. So we see that for AR, the slope is about 1.5 times R. So the CV bar is about 1.5 times R. For neon, it's like exactly 1.5 R, no matter what the pressure is. Again, and similarly for nitrogen, we see a little bit of slope, but for nitrogen, it's basically exactly 2.5 times R is what the molar constant volume heat capacity is. For O2, we see a little bit of a different behavior here, right? If we look at O2, we see some deviations here. Even though the line looked pretty straight when we were looking at just the line of U versus T, we can actually see that we have a slightly bigger slope of the line out here. That means that slope of that line, which looked pretty linear, was actually increasing a little bit as we got to those higher temperatures. So yeah, this is a nice way to sort of really get that information. Largely confirms what we had from the previous plot, but now we have some additional information, right? O2 here has this changing heat capacity. We see that its heat capacity is getting a little bit bigger as we go over to high temperatures, whereas the other ones are, again, are largely constant. So again, just all from experiment now, we have these 4 data points. When people measure other gases, they actually find very similar behavior. It turns out that it's very useful to have this approximation. It turns out that largely we find that CV is independent of pressure for ideal gas, right? So again, ideal gases we don't have. That's a common approximation, that it's independent of pressure. We see that here. That's going to be true at sort of moderate or low pressure. And we have CV bar is basically roughly equal to, maybe I'll put a rough approximate, but this is basically equal to 3/2 R for a monoatomic ideal gas. Again, calling it an ideal gas, that's basically just saying that anywhere the ideal gas law applies, this is likely to be a good approximation. So ideal gas law is going to apply at low or moderate pressure. We'll sort of verify that a little bit later, but yeah, sort of a good fact to know. For diatomics, it's going to be approximately equal to 5/2 R. But only at low temperatures. We see from oxygen as the temperature increases, it actually does increase over that 5/2 R. The sort of formal limit on this is related to content that we did earlier. This is going to be at temperatures much less than what's called theta vibration. So this is the vibrational temperature. That we get by just converting the vibrational energy or the delta E between the vibrational levels into Kelvin. Okay, our next step then is using the approximations that we just developed, and it's convenient to just define the internal energy of an ideal gas at 0 Kelvin to be 0. What is the internal energy of one of these gases as a function of temperature T? Okay, so first let's look at this sort of from a graphical perspective. If I have U and T, or now maybe I'll do U bar again. What we observed was this was linear. With a slope of, again, since it's U bar versus T, the slope of this is CV bar. which is equal to the derivative of U with respect to T, holding everything else constant, volume and moles. So that's the slope is CV bar, and that CV bar is basically constant under these normal conditions. So we can write then that U at some later temperature is equal to, since this is just the equation of a line, is going to be equal to CV bar times T plus, what's the y-intercept? Well, we're defining this, I guess this is U bar here. We're defining that at 0 Kelvin, the internal energy has to be equal to 0. So this is plus 0. So U bar of T is equal to CV bar of T. We can get rid of the bars here by multiplying everything by N, right? Since U is equal to U bar, since U over N is equal to U bar, U is U bar times N, CV is CV bar times N, where N is moles. So now I can write U is equal to, I need to multiply both sides by N, so multiply both sides by N. CV bar times N is CV bar, so U is CV times T, which again, we can plug in the 2. This applies to monoatomic and diatomic below much less than theta vibe. Again, we have to have ideal gases here. That's sort of what we're part of the assumption here. The ideal gas behavior is that there's no dependence on pressure here. Okay. Then again, plugging in, the 2 different results we get are that U, plugging in for a monoatomic ideal gas, CV bar is 3/2 R. So CV is 3/2 nRT for a monoatomic. And U is equal to 5/2 nRT for a diatomic ideal gas. And again, this is at temperatures much lower than the vibrational temperature. These are very nice results. These let us say that, again, from experiment, we know that now that there's an ideal gas, monoatomic, diatomic, I guess I'll get ideal gas there. No dependence on pressure, it just depends on temperature. Higher temperature, more internal energy. And again, for a monatomic ideal gas, we have this relationship. For a diatomic, we have this other one. This is really useful for ideal gases, figuring out how internal energy changes in a lot of different processes, because all we need to do is see how the temperature changed. Okay, let's end with one more sort of proportional thinking example. Again, remember that we're always going to basically be allowed to assume ideal gas behavior. What is that final pressure?